In problem 98, we study the green vehicle routing problem. The core idea is to build delivery routes that are not only efficient in operating cost, but also explicitly optimized for environmental impact. In practice, this means you may accept a slightly longer or more complex plan if it reduces total emissions. This problem is especially important when your fleet includes electric vehicles where feasibility depends on battery range and charging availability. This slide explains why green routing matters. Traditional routing focuses on distance, time, or the number of vehicles. But emissions are an additional objective with real regulatory and customer consequences. For diesel vehicles, emissions and fuel use depend on more than distance, including load and congestion. For electric vehicles, the limiting factor is battery level and charging time, so the route must be both green and feasible. The scenario is a courier company called Eco-Deliver. The company operates in a city and is redesigning its daily routes to reduce its carbon footprint. The fleet includes conventional diesel vans and a new electric vehicle fleet. Diesel efficiency varies with load and traffic, while electric vehicles must manage range and recharging. The goal is to deliver on time while reducing overall emissions. This chapter uses a tiered toolkit. Tier 1 builds a multi-objective mathematical model that minimizes both distance and emissions. Tier 2 uses a modified savings heuristic that blends distance and emissions into one merge score. Tier 3 uses a population meta-heuristic called the Sine Cosine algorithm. Tier 4 introduces reinforcement learning for dynamic routing. Then tiers 5 through 9 extend the system using simulation, autonomous negotiation, human decision support, ethical constraints, and quantum optimization. Tier 1 is the formal baseline. We define a routing decision variable that indicates whether a particular vehicle travels directly from one node to another. We then minimize two objectives at the same time: total distance as a proxy for operating cost and total emissions as the environmental objective. Constraints ensure every customer is visited exactly once and that each vehicle route is operationally feasible. This slide defines the sets. We have a set of vehicles and a set of customer nodes. We also define an extended node set that includes the depot as node 0. Operationally, these sets let us express routing decisions across vehicles and across all possible travel arcs between depot and customers. This slide lists the parameters. Distance captures how far two nodes are from each other. Emissions represent the environmental impact of traveling between the same pair of nodes. Each customer has a delivery demand, and each vehicle has a capacity limit. In a real system, emissions can depend on load and congestion, but the model can treat emissions as edge values or as functions built on more detailed inputs. The decision variable is binary. It equals 1 when a specific vehicle travels directly from node I to node J, and 0 otherwise. This variable is the fundamental building block for both the objective functions and the feasibility constraints, since it defines what edges are used in the final routes. The first objective minimizes total distance traveled. You sum distance over all used arcs in all vehicles. This objective acts as a proxy for operating cost, since distance typically correlates with time, labor, fuel, and wear. Even if you care primarily about emissions, distance remains important because it directly affects productivity and service level. The second objective minimizes total emissions. You sum the emissions associated with each traveled arc. This captures the environmental goal directly. In practice, the company can tune the balance between the distance objective and the emissions objective by using weights or by applying a multi-objective decision rule. These constraints enforce visit once and flow conservation. Visit once ensures every customer is served exactly one time, which prevents both missed deliveries and duplicate service. Flow conservation ensures route continuity for each vehicle. If a vehicle arrives at a customer, it must also leave that customer, preventing disconnected paths that do not form a valid tour. This slide shows the depot, capacity, and subtour constraints. Each vehicle must leave the depot once and return to the depot once, which defines a complete tour. The capacity constraint prevents overloading. The subtour elimination constraint prevents the model from creating small disconnected cycles that ignore the depot. Together, these constraints translate a mathematical solution into a physically executable route plan. This example illustrates the trade-off. With a depot and two customers, you can compare candidate routes by their distance and their emissions. A route can be cheaper but dirtier, or greener but more expensive. The value of the green vehicle routing problem is that it forces you to make the trade-off explicitly, rather than assuming the shortest route is always the best route. This figure visualizes the trade-off between a greener route and a cheaper route. The picture is a reminder that cost and emissions can respond differently to the same geographical choice. In a city, a slightly longer highway segment may be cleaner than a shorter stop-and-go urban segment. So distance alone is not enough to guide decisions. Tier 2 uses a modified version of the classic savings heuristic. The process starts with one route per customer and then merges routes to reduce overall cost. In the green version, savings are computed as a weighted combination of distance savings and emissions savings. This makes the merge logic directly reflect the company priority between cost and environmental impact. This slide shows the composite green savings formula. The first part measures how much distance is saved by connecting two customers instead of serving them separately. The second part measures emissions savings with the same structure. Two weights control the balance. If the emissions weight dominates, the algorithm behaves like an emissions-first heuristic, even if the distance outcome is not minimal. Here is the heuristic logic in words. You compute composite savings for every customer pair, sort the list, and attempt merges from highest to lowest. A merge is allowed only when it keeps the route feasible. That means respecting vehicle capacity and, in an electric vehicle setting, respecting range and charging feasibility. The algorithm stops when no further merges are feasible. In this part, we move from the idea to the mechanics of the implementation. You will notice logic related to demand, objective. As you read it, follow the data flow from inputs to outputs, and pay attention to how the state is updated. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to validate this chunk against a small hand-computed example so you can trust it before using it in production. In this part, you can see the implementation details in action. You will notice logic related to demand, route. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to print or log a few intermediate quantities, so you can verify that the update logic behaves as expected. The Sine Cosine update rules show how an agent moves relative to the best solution found so far. In one mode, the update uses a sine term, and in the other mode, it uses a cosine term. Random parameters control step size and direction, which helps exploration. Over iterations, the main step parameter decreases, so the search gradually becomes more focused on refinement near the best candidate. This figure gives a conceptual view of search agents moving toward the current best solution. Early in the run, agents spread out to explore the solution space. Later, the population collapses towards strong solutions, improving the best plan found. In a green routing setting, this helps navigate a rugged landscape created by capacity and energy constraints. Tier 4 uses reinforcement learning for dynamic decisions. The key modeling step is representing routing as a sequential decision process. A practical state includes where the vehicle is, how much battery remains, and which customers are still unvisited. Actions include visiting a customer or visiting a charging station. The reward encourages low cost and low emissions while penalizing infeasibility. This slide focuses on Tier 3. Conceptual search agent movement. Key points shown are Sine Cosine. Algorithm search agents move toward the best found solution. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits. And confirm reported results are consistent with the scenario and the objective. This slide summarizes the conceptual learning loop. The agent interacts with the environment over many episodes. It chooses actions with exploration, observes rewards and next states, and updates its value estimates. Over time, the agent learns a policy that tends to choose actions that produce efficient and green routes without violating operational constraints. Tier 5 introduces a digital twin, a high-fidelity simulation that mirrors the fleet and the city context. The twin can include detailed vehicle energy models, live traffic and weather, and energy grid conditions. This makes it possible to evaluate both cost and emissions outcomes before committing to a real-world route plan. This slide focuses on Tier 4, Conceptual Q-Learning Loop. Key points shown are: initialize a value table for state and action pairs. Run many episodes starting from the depot. Choose actions with an exploration strategy and observe rewards and next states. Update the value estimate using the Bellman-style update. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits. And confirm reported results are consistent with the scenario and the objective. Tier 6 decentralizes control into a multi-agent negotiation system. Vehicles can bid for tasks based on their marginal cost and marginal emissions. A contract net-style protocol allows tasks to move dynamically to the cleaner or more feasible vehicle, which is especially valuable under disruptions like unexpected congestion or a low battery event. Tier 7 is a human and artificial intelligence partnership. Instead of returning one single plan, the system produces a set of Pareto optimal plans. The dispatcher can then choose the plan that best fits real constraints, such as high-priority customers or service risk. Explainable notes help the human understand why a plan is cheaper, greener, or balanced. This figure represents Pareto frontier decision support. A balanced plan is often the best operational choice, even if it is not optimal on cost alone or emissions alone. The value of the advisor is that it exposes trade-offs clearly and allows the human dispatcher to apply contextual knowledge, such as customer sensitivity to delays. Tier 8 introduces value alignment and fairness. Without constraints, an optimizer may route polluting vehicles through vulnerable neighborhoods, creating unfair exposure. A fairness constitution adds hard limits or penalty terms. The system checks route plans against these principles, rejects violating solutions, and reruns optimization. The extra expense can be tracked as the cost of fairness. This slide focuses on Tier 7, Pareto Frontier Decision Support. Key points shown are: human dispatcher selects a compromise plan using artificial intelligence explanations. Operationally, use these points as a checklist. Confirm the definitions match your data. Confirm constraints reflect real limits, and confirm reported results are consistent with the scenario and the objective. This slide shows the QUBO objective structure. Binary variables indicate which customer appears at which position for a particular vehicle. When two consecutive positions in a tour are assigned to two customers, an objective term adds the weighted distance and emissions for traveling between them. In this way, a routing cost becomes a quadratic function over binary variables. This slide shows how constraints become penalty terms. A visit once penalty forces each customer to appear exactly one time across the tour positions. A position fill penalty prevents multiple customers from occupying the same tour position. The penalty coefficient must be large enough. If it is too small, the optimizer may prefer an infeasible solution that looks cheaper in the objective. These practice questions help you apply the ideas from every tier. You compare routes under a weighted objective, simulate a first merge step in the savings heuristic, and propose an encoding for a meta-heuristic solution. You also define a reinforcement learning formulation, propose digital twin what-if tests, evaluate a multi-agent bid with a utility function, and reason about fairness and quantum penalty tuning. To close, the green vehicle routing problem expands classical routing into a joint decision about cost and environmental impact. Formal models provide a baseline, heuristics, and meta-heuristic scale to larger instances. Learning and simulation add adaptability, and ethics and quantum mappings extend feasibility and search. The practical goal is a route plan that is executable, cost-aware, and genuinely greener. This slide continues the structured explanation of green vehicle routing. Focus on the operational meaning of what is shown and how it affects route feasibility, emissions, service reliability, and total cost. This slide continues the structured explanation of green vehicle routing. Focus on the operational meaning of what is shown and how it affects route feasibility, emissions, service reliability, and total cost.